All right. Sorry, the screen is a little yellow. I'm not sure what's causing that. But we are going to work on solving exponential equations using logarithms today. And you are going to want to use your calculator. So if you don't have a calculator out, I would get one. And it can be scientific or graphing. Either one will do this. And while you're grabbing your calculator, I'm going to work through these two review questions. This is just having us convert exponential form to log form, and that's what's going to help us solve these equations today. So just to remind you guys, in the exponential form, the base of the exponent in this question here, this is a true statement, 8 squared is 64. The base of the exponent is going to swing across the equal sign. That brings the exponent down on the level with the rest of the equation. And the way we write that is log base 8 of 64. So this is also a true statement. The base of the exponent becomes the base or the subscript of the log, and you just kind of scooch the 64 down and put a log in front of it. Okay, kind of the same thing here. This is a true statement. 2 to the negative third power is equal to 1/8. You just swing that base of your exponent, the 2, across the equal sign. It brings the 3 down on the level with the rest of the equation. And we're going to write log base 2, base of the exponent becomes the base or the subscript of the log, and then the 1/8 there to the side. Now, both of these are true statements. What we're going to work on today, we're going to have variables in one of these locations. And so because your calculator can only do log base 10, we're not going to be able to type in log base 8 of 64 or log base 2 of 1/8 like we had in the little example there. So what we have is called the change of base formula, and that's what we're going to talk about next. Oops, sorry guys, I got a little thing in the way there. Okay, so here's what we're doing. Change of base formula. I'm going to use, these all have to represent positive numbers, M, B, and C. B cannot be 1, and C cannot be 1. So I'm going to write the log base B of M, and we could, of course, replace those with numbers, which I'll do here in a second. Now, what we can do is do the change of the base. So I'm going to do log base C of M over log base C of B. Now, what we usually do for the change of base formula is we choose C to be 10. That way we can do that on the calculator. So, for example, and you guys could check this, we did these by hand. The log base 5 of 125. Now that's written in base 5. So what I do for my change of base, and I'm just going to write log, and remember, if we don't write the little subscript, it's assumed to be base 10 divided by the log of 5. And then we can go ahead and grab our calculator and check that real quick. So, okay, sorry for the cut. For some reason, when I put my calculator in there, it made the screen go black, so I backed it up a little bit. I'm just going to show you here, if we evaluate this log base 5, 125 by hand, what we did was we changed that to exponential form, swung the base over. 125 is 5 to the x, and then 5 to the third, 5 to the x. So then we said, okay, that is equal to 3. So log base 5 of 125 is equal to 3. So now if I have my change of base, you're going to find your log button on your calculator. And if you've got a graphing calculator, just move this back just a little bit. The log button is right next to the 7. And I'll zoom that back in. So I'm going to do the log of 125. And it's really important there, you got to close your parentheses, and you guys cannot see my calculator screen there, it's focusing in. Okay, and then I'm going to divide that by the log of 5. So hit my log button and 5. And you guys should see there that that result is 3, which is what we have. All right, so the rest of this is just some practice. So I'm going to write this out, and then I'm going to grab my calculator and evaluate. So I want to change the log base 6 of 12 to base 10. So I just do the log of 12 divided by the log of the 6. And remember, if I don't write the subscript, that's going to be a base 10, so we can do it on the calculator. Whatever you're taking the log of in the original goes on the top, and then the log of whatever the subscript is, that goes in the bottom when you set this up. So this is going to be the log of 400 divided by 5. And then this last one, we're going to do the log of negative 20 divided by the log of 3. Now, before I grab the calculator, I want to say right here, this last one is going to be no solution of any kind. I can't simplify that because you cannot take the log of a negative number. If you tried to type that in your calculator, it wouldn't let you. Now, the other ones we can do. So again, sorry, this is going to probably mess up the lighting on the calculator. So I'm going to do, and these are going to be kind of nasty numbers. Okay, sorry about that, guys. I'm trying to adjust these lights so you can see. So I'm going to do the log of 12, close the parentheses, divided by the log of 6. Okay, so this is going to ask you to round to the nearest thousandth. That's 3 decimal places. So I'd say 1.387 to check to show you what I'm doing here. If we did this the way we did before, log base 6 of 12, and I set that equal to x, there is no way you are going to rewrite that and get 6 to a power equaling 12. But let me show you real quick, that answer we just got would solve that equation. And it's going to be, whoops, if I do 6 to that power, 1.387. Now we rounded a little bit, so it's not going to be exactly 12, but you can see it's extremely close. And if I had written out all those decimal places, it would have worked. So that's what we're doing when we do this change of base. And then we'll just do one more real quick. If I do that log of 400, close your parenthesis, divided by the log of 5. There we go. And I'm just going to go 3 decimal places here, so that would be 7.2, and that's going to round up 3, and that's going to be my answer. So if you get weird decimals, just going to go 3 decimal places is what it should tell you, and don't think you're doing something wrong because a lot of these do have decimal answers. Okay, now what's the purpose? The purpose is using this to solve exponential equations. So exponential equation just means an equation where the variable's in the exponent. So I have 3 examples here. 5 to the x equals 16. What I want to do is I need to bring that exponent down on the level with the rest of the equation. And the way to do that is to convert that to log form. So I'm going to swing this across. That exponent of x then comes down on the level with the rest of the equation. Now, the base of the exponent becomes the base or the subscript of the log, and then log of 16. Now, I'm just going to do change of base, do log of 16, divide by log of 5, and then that should be your answer. So we're just grabbing the calculator here. Log 16, close your parentheses, divide by log 5. Whoops. And we're going to go 3 decimal places. So in this case, 1.723. And then you can, of course, plug that in to check. And again, I rounded, so it might be a little bit off. But if I do 5 to the 1.723 power, you're going to see it's super close to 16, a little bit off because of the rounding. Okay, so same thing here. I'm going to bring this into log form by swinging the base of the base of the exponent to become the base of the log. Now, this question will have an extra step because my exponent's a little more complicated. So we're going to do log of 21 divide by log of 6, and then log 21 divide by log 6. Now, we don't want to round multiple times here, so there's my answer if I do the change of base. And that's equal to 2x. So then what I need to do is take that and divide by 2. So I'm just taking my answer, just hitting divide by 2. And then this is what I want to put down to the nearest thousandth, which is, again, 3 decimal places. Now, that 5 is going to round that 9 up. And so we're actually going to just put to the nearest 10,000, or sorry, the nearest thousandth, we're going to put 0.85. I've got one more here. The entire exponent is x plus 4. So when I swing this 3 over here, that x plus 4, that expression is going to come down. So log base 3 of 101. And we can do our change of base. So we can do this on the calculator. Log of 101 divided by the log of 3. So log 101 divided by log 3. Okay, now this is x plus 4 equals what I had there. So what I want to do in this case, I'm just going to need to subtract the 4. So if I subtract 4, whoops, and so minus 4, this minus 4, then my answer to the nearest 3 decimal places, we're going to go 0.201. And these are very easy to plug back in and check in the original equation. A couple more complicated equations here on the back. So I've got 3 times 5 to the 2x minus 9 equals 111. So get rid of any addition or subtraction first. So I'm going to add that 9. That'll give me 120. Now, biggest mistake people will make here is they'll accidentally multiply that 3 and 5 together. The only thing being taken to that exponent is the 5, so you do not want to multiply these. What you actually want to do is you want to divide by 3. So I get 5 to the 2x is equal to 40. Then I'm just going to swing this guy over. That brings the exponent down on the level with the rest of the equation. Base of your exponent becomes the base of your log. Forgive me, I should have left us a little more space. We're going to do change of base, so we can do this on the calculator. Log of 40 divided by log of 5. Whoop. So I'm just going to grab that log of 40, close the parenthesis, divide by log of 5. And then we're going to end up, because that's 2x, I'm going to divide that by 2. And then I'm going to route my answer to 3 decimal places. So here I'm going to say x is 1.146. Again, you can easily plug this back in to check. And then let's do one more. I'm going to subtract 12 here. So I have negative 4, 2 to the 3x minus 4, a little bit complicated of an exponent here. Now, if I subtract 12 from 172, I get 160, divide by negative 4. 2 to the 3x minus 4. This would be negative 40. I'm going to bring that exponent down on the level with the rest of the equation by converting this to log form. Now, this is the log base 2 of negative 40. And if you guys remember, you are not allowed to take the log of a negative number. Like if I just try put that in right now, log of negative 40, it'll tell you it's an error. Okay, so I'm going to put no solution for this question. Anytime you end up trying to take the log of a negative number, you are not allowed to do that. It's not possible to get that value to be a negative, so you can stop right there and just say no solution. All right, now the rest of our lesson is going to be a little bit of a throwback to writing some exponential equations. So I'll just write those as we go through. The first one says lunch at your favorite food truck costs $6.50. The price of lunch has steadily increased 4% per year for many years. After how many years will the cost of the lunch be $10? So let me remind you, general exponential, y equals ab to the x. In this case, our initial amount is going to be what we're paying for lunch at the food truck, which is going to be the $6.50. Now, this is saying I have an increase in price. So b is going to be a growth here, so it's going to be 1 plus that rate. So 1 plus 4% would be 0.04 as a decimal. We got to convert that. And so my b is going to be 1.04 here. Now, this is interesting. So our variable is actually going to be x, which is the exponent here. X is representing time. And so I know what I want the lunch to cost. It says after how many years will the lunch cost be $10? So what we're actually going to do is plug in 10 for y. So my setup would be 10 equals 650, or you could just put 0.65 if you want to, 104 to the x. Now, the first thing you got to remember, do not multiply these numbers together. That's the most common thing people will do. What we actually want to do is I'm going to divide both sides by that 650 or 6.5, however you want to write it. So if I do 10 divided by 6.5, I'm going to go ahead and leave that in that format because I don't want to round multiple times, and that's not a nice decimal. So I'm just going to leave this right like this. And what we want to do here, we need to bring that exponent down on the level with the rest of the equation. So I'm going to swing this here. this is going to be the log. The base is going to be that 1.04, and I'm going to leave that 10 over 6.5. So we're not rounding multiple times as we go through here. Now, this is just going to be a few more buttons to type on the calculator. So I'm going to use my change of base. Forgive me, I should have written a little bit smaller. We're going to do the log. Now, I'm going to do base 10. So I'm going to put that 10 divided by 6.5 on the top. And then I'm going to do the log of that 1.04. So when I type this in, that way we're not rounding multiple times. Make sure you don't try to use a fraction button if you're using a scientific calculator, because it will not do that if you've got a decimal. If you're using a graphing calculator, you can just type it in right like what I'm doing. Divide by the log of 1.04. And I'm going to get x is about 10.984 if I continue with my rounding to the nearest thousandth. So I'm just going to go back and read the question here. It says, after how many years will the cost be $10? I would say that's really close to 11. So I'm going to say it's going to take 11 years for that 4% increase to raise that lunch price to be $10. Okay, my next example says you bought a car for $15,000. That's going to be your initial amount. The car depreciates, so that means you're going to have decay. So it's going to be 1 minus the rate. So it decreases at a steady rate of 6.5%. So this would be 0.065 as a decimal. And when is the car going to be worth $10,500? That's going to be our y. So our general format, y equals ab to the x. I know what y is. I know what a is, so I'm going to sub those in. I want to know when the car is worth $10,500. I bought the car for $15,000. 1 minus the rate here. I'm just going to grab my calculator real quick for that. We're going to do 1 minus that 0.065. So the car holds about 93.5% of its value every year. And then your exponent, we're going to figure out how many years this is going to take. Now, again, don't multiply, you want to divide here. And this is totally up to you. You can reduce that fraction if you want to, or you can just leave it right like that. It's your choice. I'm just going to go ahead and leave it. So I'm going to do the 10,500 divided by 15,000. This is 0.935 to the x. Now, the only way to get my exponent down on the level with the rest of the question is to turn this into a log. So we're going to swing that base of the exponent to the other side of the equation, and I'm going to write it over here. So the base of my exponent, that 0.935, becomes the base of my log. Now, I didn't simplify this, so I'm just going to leave that alone. And then that'll be my exponent, which will be the number of years that this will take. Now, to be able to do this on my calculator, we're just going to do change of base. So instead of that base being that 0.935, we're going to change these both to base 10. And to do that, using my change of base theorem, and that's all I got to type into the calculator. So log 10,500 divided by 15,000. And then I want to divide that by the log of 0.935. Hit equals. And then we'll go, whoops, sorry, the light's in the way there. We're going to go 3 decimal places here as we write this out. 5.307. And so we're saying, when is the car going to be worth 10,500? We're going to say about, I would say about that 5.307 years, unless it tells you to round differently. And I have one more example here. Now, this last example is going to deal with a half-life. So I just want to remind you guys, the half-life formula, it's the time it takes a substance to cut in half. So anytime you have a half-life, I automatically know the B value is going to be 0.5 or 50%. The other little alteration, it's the time over the half-life is your exponent, so it's a little bit more complicated than just a basic exponential, so keep that in mind. So this says the half-life of a substance is 2.45 hours, so that's obviously the half-life. You have 100 milligrams of the substance to start. Your starting amount is going to be your A value. About how long will it take the substance to have 75 milligrams left? So I want to know when I have 75 milligrams left. That's what we're going to plug in for Y. So in my general form here, I'm going to have 75 equals 100 times 0.5 to the x over the half-life, which is 2.45. Okay, this is going to be one extra step than the previous questions we've been doing. So 75 divided by 100, if you do that, that's actually a decent value. So I'm just going to go ahead and reduce that right now. That's 0.75. And this will be 0.5. Now that exponent is a fraction. So to get that exponent down on the level with the rest of the question, the only thing to do, base of the exponent becomes the base of the log. And we'll do our change of base here, so we can do this on a calculator. Log of 0.75 divided by the log of 0.5 equals x over 2.45. Now, let me grab my calculator. I'm just going to have one extra step here. So the log of 0.75 divided by the log of 0.5, that's a decimal here. Now, to get this 2.45 out of the denominator, I just need to multiply both sides by that. So I'm going to do that directly on the calculator here, times 2.45. And so I'm going to go 3 decimal places like I've been doing. 1.017. So this says about how long will it take for the substance to have 75 milligrams left. Since the half-life is in hours, our answer would be approximately this 1.017 hours for that to happen. If I take this guy right here and evaluate like we did by hand, we have log base 5 of 125. We'd set that equal to x, swing that base. We'd get 125 is equal to 5 to the... Oh,